Energy efficiency is a huge topic. Buildings use up about 40% of overall energy here in the U.S. Out of that, about 40%-ish of that 40% is used on heating and cooling of buildings. So that's a big part of making sure that the building is comfortable, it can be lived in, can be nice to come in and buy stuff. And so the building envelope and the technologies that we use to keep the building cool and warm and navigating all of that is extremely important. And so today we have three great companies who are developing the next generation set of technologies that will be greatly improving the efficiency and the management of our heating and cooling. So with that, we'll launch right into each of the presentations. Our first presentation will be Phase Change Materials. Will be Chris Martin, who heads up their business development. Phase Change Material has actually been around for over 25 years, and started as the material that keeps your pizza warm, and it's now keeping our buildings warm. So,
here's our factory. It's in North Carolina, so you know, U.S. made. Basically, what I want to do is kind of go over the basics of phase change, talk a little bit about the enclosures of the mechanical systems, and then quantify the savings a little bit for the materials. My background, by the way, is I'm an architectural engineer out of CU Boulder, and my mechanical engineering license is in mechanical HVAC design. So my professional career, for the most part, has been what maybe some of you are doing now, is HVAC design for mechanical systems for commercial buildings, hospitals, clean rooms, the whole deal. I found this phase change product about a year ago. A colleague, acquaintance called me from back east, said, "Hey Chris, I'm thinking about selling this stuff. I'm not a energy guy. Can you look into it, make sure it's not snake oil?" So I said, "Yeah, sure, I'll look into it." And then basically I fell in love with it, decided to help take it to the market. So that's kind of my background. So the current environment, I'll go through that pretty quick. But basically we're all about energy, like most people in this room. But the current environment, what we're finding is architects are demanding a more competitive products, and the building owners are demanding energy efficient buildings. So that's kind of the gist. So the solution that we've brought to the market now is what I like to use the term a smart thermal mass. So a smart thermal mass is the ability of a material to absorb, store, and later release heat or energy at a rate that's roughly in step with the cycle of a building, whether the cycle of a building being the sun that's striking it, or the heating or the air conditioning system. So that's as opposed to a dumb thermal mass, which might be like a concrete, which basically does an average. So with a phase change, that's what we're doing here. If I had one slide, this would be it. This shows a building. The black line is the ambient temperature. You can see it goes, this is a building that's built to code, no heating on, no air conditioning on. The black line shows the outdoor temperature at 49 degrees and then up to 86 degrees. The red line will show a building, this is through Arizona State Utility that did this, is a building that's with no phase change material. You can see that it gets cold, gets down to 58 degrees and then up to 83 degrees, which kind of makes sense because of the thermal mass of the building. It's not getting as cold or as warm. And you can also see the lag a little bit on when the different cooling and heating peak times were. And then the green line is a building with phase change in the walls and up in the lid. So what we're doing here is just by putting phase change in the building, we're able to reduce the temperature swing down to a 4-degree temperature swing in a building just by the phase change absorbing and releasing its heat. Some of the sustainable natures of the product, it's all made from natural products. It's primarily soy and palm oil. It is 100% biodegradable, LEED compliant, and it is naturally a fire suppressing product. The soy and palm oil, why that's might be important to some of you that know the history of phase change. Back in, well, what's in the market now, there is a paraffin-based product, phase change product, primarily over in Europe, DuPont and BASF. It doesn't work as well as this, but it works fairly well. It's about 4 times the cost of our product, and also the flame spread ratings of the paraffin or the petroleum-based product don't really work out so well in the United States, so we cannot get that product into the codes. So when we came out with this soy and palm oil, we solved a lot of the problems. The other problems, or the product that you might be familiar with phase change, is the salt-based products, which really came out in the early 80s, and actually the whole industry was relatively excited about it. The challenge was it broke down in 3 to 5 years, and it stopped going through the cycling, so it kind of went away. So, but the life of our product, I probably have a slide on it, but just in case I don't, we've cycled the product from minus 60 degrees Celsius to positive 60 degrees Celsius over an equivalent of 85 years, and it's still performing the same. So we've got the life of the product figured out as well. Well, actually, there's some cost comparisons, about 4 times more is the petroleum-based, long life, adaptability, so we can put it into buildings in a lot of different situations. More on the sustainability of the product. These are just some LEED compliant points that you can possibly pick up with the phase change material. So how does it work? Probably try to spend a little bit more time on this than the other slides. But basically how phase change work, it acts as a thermal mass. There's thermal mass in buildings, and there's thermal resistance. Thermal resistance is our R value. And R value is an R value, whether it's minus 20 degrees or 110. If a wall's an R19, equivalent R19, it's always an R19. With phase change, what we're really doing, it acts as a thermal mass. So mass acts differently than resistance. So, so I kind of like to think of it, you know, insulation's like a thermal resistor, kind of just slows the energy to go down. And phase change or mass, what it does is acts as a storage unit. So again, another good slide of the product. The product is sold currently. We put it into a building in several different applications. But typically it's 16 inches wide by 8 feet long. 16 inches wide, you know, normal spacing of the studs of a wall. So I'll show you some slides here in a minute, but so this would be stapled to the studs, and then the sheetrock would go up right up against it. That would be one application. So I do have some samples up there to show the actual, you know, I cut up some samples. I don't have enough, but I do have business cards. If you didn't get a sample, you want one, send me an email and I'll mail you one. Basically, energy is always moving until we're at absolute zero. So the product right now is probably absorbing energy right now from the lights and from the people in the room, and then it's releasing energy later on. So we package it. This is for those of you who are familiar with the industry. These are some of the common temperature ranges. 69 up to 84 degrees is when it does its transition, when it really starts to transition. The Department of Energy wants us to market this product or sell the product in M as in Mary, in M27, M51, M91, M182. And all that means is how many BTUs per square foot the product can absorb or release when it goes through a full transition. So our M27 and M51 are the most common for building applications. And so it's about 91 BTUs per pound for latent heat. So this product that you see up there on the table is equivalent to about 10 inches of thermal mass energy as of concrete. So I'll give you an idea. So we're getting that much energy in it. We have it in Class A and Class C. So this just shows you another example of the performance characteristics of phase change compared to some other thermal storage materials, wood and plastic and water. So this is a good graph for to really get a handle on what happens. You can see one of the vertical line, the diagonal line is the thermal water energy storage, and it's pretty much consistent. But see what happens with the phase change material at a specific temperature. So this one's transitioning at 27 degrees Celsius. So what happens when it hits 27 degrees, the ability of a product when it transitions to absorb and release a significant amount of energy changes a lot. So this is why this is so important. What's kind of interesting in here and critical as far as our engineering is concerned is we do that. You can see we do that transition in a relatively tight range. like 1.5 degrees Celsius, which is good because then that gives it its smart characteristic, if you will, because as building scientists and architects and engineers, when we want something to happen, we want it to happen at a relatively tight range for it to release or absorb the energy. So 1/2 inch of phase change, equivalent to about 10 inches of concrete. I don't particularly care for this slide because it's comparing it to insulation, and their R value and thermal mass are different units. But when this product is transitioning, it does have what I use, well, the industry might use the term as equivalent R value, but you won't see R value talked in our literature. But when it's transitioning, your wall, your roof is doing an equivalent transition of about 36 inches of insulation. And there's some steady state heat transfer calculations that show how we came up with that 36 inches of equivalent insulation. Now, I want to show you a couple. So basically, all it does is, what's kind of neat about this is the higher the temperature is away from whatever your set point temperature in the room is. Let's say in this room it's 73 degrees. Whatever the outdoor temperature is, the further it is away from the set point temperature, when it's going through that transition, the better the equivalent R value of the product will be. So it's more of a dynamic. So this can take a little while, these case studies, but I do have a zip file if anyone wants all the case studies and wants to read hundreds and hundreds of pages of research on phase change. But I'll go through them. This is one of the Arizona State Utility case studies and their conclusion. This shows a transition of, this is part of their research that shows the green bar is the building with phase change and the red bar is the building without phase change throughout the year. So if someone says, what's the average energy savings? You know, we're probably somewhere around 20 to, could be higher, 30% energy savings on a building. This is the exact same slide, but all we did here is put CT clamps on the outside air condenser. So we can see when the building on the top has no phase change in it, and you can see in order to keep that building at set point, that outside condenser was running pretty much full tilt from whatever that is, 2 to 6 o'clock, 2 to 7 o'clock. And the building with phase change was able to cycle on and off. Okay, this is really conceptually the most engineering that I'll get at this presentation. You can see the significant energy savings. A couple things that are important to maybe many people in this room is a lot of the energy savings are happening at peak times. You know, the 4 o'clock, 5 o'clock, this is when our KW demand's high. Depending on the utility, the KWH charge might be higher as well. But look what happens at 8 o'clock, 9 o'clock, 10 o'clock, and only in this particular building, is that now the phase change building might be using more energy. So this doesn't happen in most buildings, but conceptually I need you to understand how the product works. The goal of when you put this into a building is to have it transition, have it go from a solid to a gel, which is in my pocket here. You can see it's really loose, it absorbed energy from my leg. So tomorrow morning at 9 o'clock, if this is up above the ceiling tile here, we want to have this product back to a solid so it's ready to handle the energy of the lights, the people, this conference room transition. So in this particular case, at 8 o'clock, 9 o'clock, maybe what they did here is they turned on the help get the energy out of the building, because it's nothing magic here. We still have to get rid of this energy. So maybe outdoor air economizer would help transition the phase change back to a solid. But at 9 o'clock, 10 o'clock, 11 o'clock, cost of energy significantly better. Any rooftop chillers that are up on the roof are going to be performing a lot better at 75 degrees at nighttime compared to 97 degrees in the middle of the day. So the whole energy savings is still significant. That just shows there's a peak KW reduction of about 46%. So the KW on buildings, anyone that does commercial buildings, I guess most of us are in Excel in this area for a while anyway. The KW on commercial buildings, they charge us KW and they charge us KWH, and anyone that's looked at commercial bills know that KW can easily be as much as the KWH. So we are dropping that KW significantly with a phase change. There's a Carnegie Mellon study that actually just came out. Talks about different. This particular study talks a lot about the paraffin base compared to biophase change compared to water. New Scientist. This is an article that came out. Affiliate Engineers, pretty big engineering firm out of the northwest part of the country, that did a pretty detailed report on the software to model this, which I want to get to real quick. Just shows different graphs on when it transitions and how tight that range can be. Okay, this is cool. This is a military application that the military is looking at. If you put one of these huge tents in the middle of Afghanistan, how do you keep the guys or the soldiers cool without running? You're not going to air condition it, so this would be an application. Just putting phase change in over the tarp, so the sun it will absorb the energy and then it'll transition and release the energy back to the night sky. Some more on that. Some different partners that we have. Raven Silk, which was our next guest speaker. We'll talk about that here in a minute. Curtain wall applications. Thermal energy storage system. Instead of doing ice storage, put a product in there, a phase change. What's new to the market with this, as far as you might be concerned, is normally ice storage is for very large projects, and now with these little containers filled with phase change, we can slide them into a 40, 50 ton application to help reduce the kW. So we're running the chillers in the nighttime, making the phase change, and then the building's pulling off the containers in the daytime. So there's some advantages. We do have some companies, Rigidized Metals, with 5-foot high cubicles. They're putting the phase change right in the middle of the cubicles, so we're adding mass to a building. Wall panels, concrete panels. We have roofing applications. These are partners that are putting our product, like Will's going to talk about here in a second, in the middle of their product. So we have roofing applications as well. That just shows the temperature fluctuation. There's a roof application. I think this is in North Carolina. Metal roof applications. So different businesses putting our product into their product. This Oak Ridge National Laboratory actually funded this with the metal roofing industry to put phase change into a metal roof application, and the savings are significant. At least a half a dozen or more applications where you can put this into a building. That shows it being stapled up to the studs and then the sheetrock. Where this product goes in this market, typically it's on the inside of the envelope, so it's on the people side of the insulation, so when it releases its heat, the energy goes back into the building. In a real hot climate, we may want it on the outside of the envelope, so when it releases its heat, we don't need it to heat up, Taos, New Mexico, or somewhere way down south. When the phase change transitions back, we want it to go to the atmosphere. This is probably our biggest project, University of Washington, 90,000 square foot building with no air conditioning, all with phase change. So we put the phase change just above the 2x4 ceiling tile. Energy heats up, phase change holds the heat, and then at nighttime these windows open up, takes the cool air from the top, runs it over the phase change, pulls the energy out of the phase change and up to a solar chimney. So they're doing a whole building without air conditioning. Very small modular net zero homes. We got this home wrapped in phase change. Churches, colleges. This is one of my projects, one of our college, Colorado projects. Down in the kitchen, we got 5-star chefs down at the Broadmoor, and the kitchen was over the top as far as getting hot. So all we did is lay phase change, just pop the 2x4 ceiling tiles and put the phase change above the ceiling tiles in the kitchen, significantly better. So another real easy application for a retrofit. And then some residential. Again, Harvard, I think they're installing this one right now. You're not going to get into those walls to do anything, but you can do it above the 2x4 ceiling tiles. So I think that's kind of it. And we'll answer questions, I guess, afterwards, right?
Great, thanks, Chris. Very exciting. Our next speaker is actually Raven Brick, and Raven Brick has a technology that's very similar in terms of the basic idea to phase change, which is, can we make our material smarter so that it adapts to our environment and can automatically cool or reduce heating for a particular building. And so, Will, Will is the co-founder and CTO of Raven Brick, and I'm happy to say part of the technology came out of the University of Colorado, and these guys have gone a long ways and is now actually building real windows. So,
Just a quick introduction beyond what it says in the slides here. Raven Brick is primarily known for our smart window product, Raven Window. We're currently building a factory, and the initial operational capability there should be in place next July. We have installations at NREL and at the GSA headquarters building in Lakewood, also Dow Chemical in Midland, Michigan. What I'm here to talk about is not Raven Window, but Raven Skin, which is our smart wall product. This has not been deployed anywhere except in some test buildings, but we thought it would be of interest to this audience. Chris really did all the heavy lifting for me in terms of describing what phase change material is and how it works. What we're talking about here is a particular application of phase change materials to curtain wall and storefront type architecture. We're talking about a region on a building where you just don't have a lot of space. In a glass building, you'll typically have windows alternating with panels that are either glass spandrel panels or they'll be insulated infill panels. But in both cases, you have to fit into this very narrow envelope. And even if you have the best insulation in the world, that's not very much of it. So the energy performance of curtain walls tends to be pretty abysmal. Raven Skin is a product that's designed to solve that problem. On a couple of test buildings, I'll show a picture of the buildings later on, but this is a glass spandrel here, and this is a Raven Skin panel. These two buildings are identical. They're placed side by side. This is on a hot summer day. And what you see is that the spandrel panel under thermal imaging looks nice and cool. Why does the spandrel look nice and cool on a hot summer day? Well, the answer is because the heat is going right through it into the building. So the spandrel's not heating up at all. That's bad. Raven Skin, on the other hand, is at the same temperature as the exterior wall of the building. What does that mean? That means that Raven Skin is effectively blocking that solar heat as effectively as an insulated wall, even though these are composite walls. They've got multiple layers, including R10 fiberglass insulation. But anyway, as you can see, the Raven Skin is growing warm, which means that it's blocking the heat from coming into the building. Now, at night, you see the opposite phenomenon. At night, this is now an inside view of the building looking out. When you're inside looking out, these glass spandrels look nice and cool once again. The reason for that is because the heat that's stored in this building is hemorrhaging out into the night through these glass spandrel panels. Whereas the Raven Skin panel actually looks warm because the heat that it's stored during the day is now being emitted at night. So you're saving energy two different ways. You're saving it during the day and you're saving it at night. Now, what does that mean in terms of the energy profile of the building? Typically in a commercial building, you have this big heat pulse that comes in the afternoon. This is year-round, not just in the summertime, but also in the winter. It's pretty typical for commercial buildings to run their air conditioning 11, 12 months out of the year. And the reason is because in the afternoon, as the sun gets lower in the sky, it starts to hit those west-facing windows, that west-facing curtain wall, and it puts a tremendous heat load on the building, and the only way that the building can respond is to kick on the air conditioner and pump that heat out. Wouldn't it be great if instead of pumping that heat out, we could store it and release it at night? Well, that's exactly what Raven Skin does. So this peak that you see, the area under these two curves is about equal. But in fact, what's happening is we're making this peak smaller, we're making it shorter, we're making it wider. What that means is that we're taking the solar heat gain out of the day when it's harmful and shifting it into the night, where in the summertime it may not be helpful, but it's at least less harmful there. In the wintertime, it's downright beneficial. Why pump heat out of the building when you're just going to have to warm your building later on? What you really want to do is store that heat and re-release it. This is the structure of Raven Skin. As you can see here, this is an 1 5/8" thick panel, and this is a schematic view of what's inside of it. So it's built like a triple-paned window. You have 3 pieces of glass that you can see here, and the overall structure of the product is kind of deceptively simple. it doesn't look like there's very much to it, and in fact, there isn't, but that's sort of the beauty of it. A lot of engineering went into making this stack this simple. What we have here is an outer piece of glass that's just part of the normal building envelope. This is a thermochromic filter. This is a material that tints when it gets hot to block the sun from coming in. This is identical to our Raven window product. It then becomes a component of our Raven skin product. This piece of glass here, this is a low emissivity glass, which means it's got a thin coating on the glass here that prevents it from transmitting long-wave infrared, which we would typically know as heat. What that means is that heat can flow, energy from the sun flows in through this structure and hits this, it's called a down converter, but in fact what it is just simply a layer of black paint that's painted on the phase change material, which is here. So in cold weather, visible light and near infrared light from the sun flow through this structure, hit this black layer, that light is converted into heat, and it's stored in the phase change material. Because of the low emissivity coating here, that heat has a high resistance to flow out this way. It has a low resistance to flow into the building. But because it's phase change material, it's only going to flow out when the interior temperature of the building has dropped below the transition temperature of the phase change material. So what we have here is several different intelligent layers that regulate very sort of ruthlessly when energy is allowed to flow into the building, how much energy is allowed to flow, and what direction it's allowed to flow. And so this deceptively simple stack has very large energy implications. Now, I'm not sure how many people here are actually in this side of the industry, but this is more for the benefit of glass companies. The same people who make glass spandrels right now, abysmally performing glass spandrels, can go into the business of making Raven skin panels. They buy the thermochromic filter from us, they buy the phase change material from Chris's company, and then the rest of it goes together just like a triple paned IGU. So it's a very simple construction. IGU, I'm sorry, stands for insulating glass unit. That's the industry term for a window. You can't use simple terms ever. And then the interior surface can be a variety of different finishes. You can use aluminum composite with epoxy finishes. You can use drywall. You can use what we've got here. This is just a piece of glass with silicone spandrel paint. This is the sort of thing that glass companies produce every day. So it's pretty flexible there. And the exterior finish, because we don't need the full force of the sun coming in to load up that phase change material, we're actually free to have a number of different exterior finishes, whether they're reflective coatings or ceramic frit, various things like that. As long as it lets about 50% of the solar energy through, that's more than you'll ever need. We have, Chris talked about R value, and this is kind of a sticking point, I think, in terms of the regulations. People say, well, what's the R value? I have a minimum R value that I need to demonstrate for any exterior wall application, so I can't get this product certified for my building unless it has a particular R value. Well, the answer is it's R100. This very skinny panel here saves more energy than R100 insulation in the same location. So that energy equivalent R value that Chris was talking about is R100. Now, if you actually were using insulation, there's no physical way, it's not physically possible to get R100 out of an 1 5/8. So what we're doing here is a lot more tricky than just keeping the heat on one side of the building. What we're doing is connecting the interior and exterior environments selectively and with a time delay to maximize the use of energy that already exists in the environment. What does this mean in terms of cost? Well, this is a glass spandrel here, very inexpensive. And if you talk about then an insulated infill panel, there's a pretty substantial cost premium. And a lot of builders are reluctant to upgrade from this structure to this structure because, quite frankly, the cost of doing so is large and the energy benefit of doing so is not very large, once again, because you don't have very much space to work with. Now, there's a lot of talk these days about putting vacuum insulation into curtain walls. This is the same kind of vacuum insulated panel that would be in a modern refrigerator. It used to be that refrigerators just had styrofoam insulation, but you want your refrigerator wall to be as thin as possible so you can get as much food as possible into the same space. And so vacuum insulation is the norm now in refrigerators. However, it's not the norm in curtain walls, and that's for a couple of different reasons. First of all, because it's very expensive, and second of all, because the added benefit of going from R10 insulation to R30 insulation is not enough to cover the cost difference. In fact, it's a very small difference in terms of the energy performance. And you know, if anyone is concerned about, I won't belabor the technical details, but you can certainly talk to me later or email me or what have you. Anyway, Raven Skin costs a little bit more than Styrofoam. It costs a little bit less than vacuum insulation. Now, why would you pay this price premium? Why would you pay so much more for this than you would for this? And here's the answer. The 10-year net savings, if you take your spandrel, your normal glass spandrel, and put low E coatings on it, well, over 10 years, this is the amount of money that you'll save, about $15 a square foot. Not bad, but, and then if you upgrade to Styrofoam, this is why people don't want to pay the premium for Styrofoam, because there isn't actually that big a difference in the energy performance. And if you look at the difference between the R10 panel and the R30 panel, well, the R30 panel performs a little bit better, but it costs a lot more, and so it actually does a little bit worse in terms of the financial return. Raven Skin is way up here. I can't really emphasize this point enough. There's actually nothing else that you could put in the building that would save as much energy or as much money. There's nothing else. There's no material that you could drop in there that would do what this stack of materials is doing. These are the test buildings that I talked about. These are tough sheds, basically. And these look like windows, but in fact, they're spandrel panels. So this one here has ordinary spandrels, two different kinds here, as you can see. And this one here has the Raven Skin panels. Now, the primary reason that we built these test buildings, the easiest way to validate the energy performance of a product like this is with computer simulations. So we use a program called Energy Plus, which was developed by the US Department of Energy. And through extensive modeling, we've determined, not only helped design the product, but also determined what the energy savings are associated with the product. That's where this graph comes from. But we need to validate the computer models. We need to have some kind of a live demonstration to show that the computer models are behaving correctly. And that's exactly what these buildings were intended to do, and that's exactly what they did demonstrate, that the performance on the buildings matches pretty closely to the performance in the simulation, and that means that we can trust our simulation results to give us the right answer. In terms of the market, I probably don't need to belabor that for this audience, but the market for glass spandrels and insulated infill panels, global market, is absolutely colossal. So we don't need very large penetration into that market to make a big difference for our customers and for our shareholders, et cetera.
Great, thanks, Will. Our last speaker is from Colorado. Colorado has developed a very innovative cooling system. In fact, many of you may have heard of the cooling system that we've deployed at the University of Colorado for one of our data centers. Using Colorado's new cooling system, we were able to save about 90% of our energy use for our data center. And this is a fairly significant sized data center which keeps track of all of our research in the Arctic world for the national government. And so with that, I'd like to invite Tony McDonald, who will give us an overview of their product and what areas they're going into.
Hi, Tony McDonald with Colorado. We are a Denver-based manufacturer of an innovative and patented type of indirect evaporative air conditioning technology. So you might be familiar with a swamp cooler. Swamp cooler is a direct evaporative. Warm air, wet media, cools the air, but it gives you a lot of humidity. Our technology is indirect. What it does is it cools the air, so it reduces sensible temperature a lot, but it doesn't add humidity. So what that does is open up a lot of interesting capabilities for you to do. So again, our technology is proprietary to us, patented by us, developed by us. We make it right down in Denver. In fact, if you're on the way to the airport on I-70 there, just past Colorado Boulevard, you might see a building with our logo painted on the side there. Okay, real quick. We fancy it's a pretty good advancement in air conditioning technology. Fundamentally what it does is it just uses a whole lot less energy than you'd use with a standard air conditioning system. typically we're going to be 100% fresh air applications. So like any technology, it has its places where it can add a lot of value and some places where it's not appropriate. But it's fundamentally going to be 100% fresh air to cool outside air as inexpensively as possible. We've been around since '99, been selling since 2003. We're in about 2,500 locations around the world. We're primarily an exporter. So we actually make stuff in Denver and ship it around the world. A lot of our product goes to Australia, India, a little bit of Africa, Europe, a little bit of South America, Mexico, and the U.S., and because our technology is evaporative, it's going to be used in a dry location. So for the U.S., we're in what we call the lower left, southwest states. We have applications in other areas of the country, but primarily that's where we are right now. Got to eat my slide. We're about 2,500 now. So we've been around a while. I've gotten some good validation from a variety of folks. And I've got a variety of reports, if you're interested, that are available on our website to see this. We've won some awards along the way, but here's my favorite. Our technology was developed by a guy named Dr. Valery Myzotsenko, who's a Ukrainian expat. And he's a genius, and he's got like 150 patents, ran one of their thermophysics research labs in Ukraine. So he gets sick of those guys and he defects to the U.S. Comes over here. The problem with Valery is he's a genius, but he can't figure out how to get this new thermodynamic cycle he's developed into a box that we can all use, right? He lives up here in thermodynamic la-la land. So he comes to Denver, meets some engineers. They work on this little box here for about 3 years, and they go to NREL, the Renewable Energy Lab, and they say, hey, we have this new technology by which we can cool below the wet bulb temperature using just evaporation. And the government experts at NREL say that's physically impossible, go away. Well, of course it works. We have it. Now they're big friends of ours, and we sell them product, and we actually hired one of their scientists last year. So how does this thing work? I'm going to do a little live demonstration if everybody doesn't mind. I'm going to turn this little hair dryer thing here on, and we'll do a little live demo. So I need a non-biased third party to come up here and look at this for me real quick. So I need a volunteer. Come on up, come on up. And I neglected to introduce my colleague Steve Clark, one of our senior engineers right here as well. Okay, James Tony. Tony. Great, welcome. All right, so what we have here is we have a little demonstration here. This is just a little tech demo, and it's really just a small version of one of our air conditioning units. So what's happening here now is that we're bringing in outside air just like you would if you had an air conditioner mounted outside. It brings in fresh air. And then in our production unit, there'd be an air filter right here. So air is brought into the unit, and we're measuring both the inlet temperature and the outlet temperature over here. So James, can you tell us kind of what we're seeing right now?
Okay, the incoming airstream is 83.5 and climbing, and the outcoming is 70.5 and dropping.
Okay, it's not quite reached steady.
84, 70. 69. Yeah, as the incoming airstream is going up, the outgoing is coming down. Can read numbers.
So essentially what this technology is going to do is this. It is going to give us a product airflow, that what we're measuring over here, at whatever the ambient wet bulb temperature is. And so what we're going to do is we're going to test that, and again we're out at what, 68, still dropping. Hasn't quite reached steady state yet. But what we're going to do now is this. We're going to go out to the desert. Now we've got units at hot, dry locations around the world. One of my favorites is Death Valley. And we have 10 units down at in their new visitor center down there. We had to fight off a scorpion last time I was down there to get to our units. I'm not joking. So let's dump some heat into this system and head on out to the desert. And James is going to tell us what he sees on the inlet temperatures.
Climbing rapidly, 89, 90, 91, 92, 94, 95, 96.
And we'll have this on later, so you can come up here and take a look at it yourself.
100 degrees, 101, 103. So it's climbing very rapidly. 107, 110, 111, 12. Yeah, it's climbing.
So we make this thing out of clear plastic for a reason. You know, we don't want people think there's any funny business. I actually had a guy at a trade show come up and say, well, not that I don't trust you or anything, but he, swap the thermometers just to make sure we're being honest.
So here's what's happening. Air is being brought into this device called a heat and mass exchanger, and two things happen in there. One, it does evaporation, and second, it does heat exchange, but it does it in one space, which makes it very efficient. So air comes in, most of the air is going to go straight through, it's going to come out on this side, that's our product air, cooled to wet bulb temperature, no added humidity. Part of the airflow is going to be diverted to this channel here, and you can't feel it, but you'll be able to come later and take a look at it. And what's coming out here is what we call working air. That's a saturated airflow, it's like a swamp cooler. We're going to push that out to the atmosphere. So we're just going to push that out. And if you come up here, you'll feel how it's rejecting heat. Do you feel that?
It's a gradient.
Okay, what are our temperatures now?
So incoming is almost 140, and the outgoing is 64.9 and dropping. That's physically impossible.
That's what they say. That's what they say. Thank you very much, James. Yeah. Here's an example of a full-size unit, about a 6-ton unit. Essentially, we see the same thing up there that we just saw. Air is brought in by a electronically commutated variable speed fan, very efficient. Air goes through a filter right there, comes into the heat and mass exchanger. The cool product air comes out the back, and the working air goes out the top. Install that wherever you need. You get that airflow for a very low energy cost. Let's see what's the advantage of what we just saw. This is a graph of energy efficiency as a function of outside air temperature. So we get energy efficiency here, and you'll hear that represented in terms like, well, SEER is one example. And if a swamp cooler doesn't actually do any cooling because it doesn't remove energy from the airflow, so there's no efficiency to be had. Standard air conditioning is going to start in the 10 range for energy efficiency, and it gets less efficient the hotter it gets outside because it has less temperature delta between the condenser coil and the outside air to drop off. Our technology, by contrast, is going to start here in the 40 range, and the efficiency is going to climb dramatically, and we just observed that. We started off doing about 15-degree delta across that unit. Later, we were doing a 60 to 70-degree delta. That means that we're doing a lot more cooling. So it's doing, in terms of tons, much more tonnage of cooling, but we didn't change the input. We're still just spinning that little fan. As a result, efficiency climbs off the roof, so that's where we're great in places like Death Valley, where it's extremely hot. How do we use it? We like to use a technology called displacement cooling. And this is a methodology by which you distribute the airflow we think more effectively. Most airflow is distributed in a building, much like we have in this space right here. You notice we got some diffusers up there. Cool air comes in, drops down on us, cools the space, recirculates back out, goes back to an air conditioner. Two problems with that. One is we're not introducing any fresh air unless we do so deliberately, so we're recirculating dirty air. The second is it constrains us to remove heat from the airflow by using an air conditioner, so you've got to put it across a coil. What we like to do is something a little bit different. If you look at a space like this, there's a thing called temperature stratification. Hotter up here or up there than it is down here. Well, we want to take advantage of that, and we want to cool just the bottom of the space with our air. So we'll bring our air in low and slow and create a pool of cool air down here at the bottom where we live. And as that air encounters heat loads like our bodies and equipment, it will take contaminants, it will rise, and instead of recirculating it, we're going to relieve it, push it to the outside. Now we can afford to throw that away because we can create that cool air so very efficiently, just using solar power if you want to. So this gives you both a very efficient airflow, 100% fresh air, it's very comfortable. Okay, a couple quick examples. Trent was kind enough to mention the National Snow and Ice Data Center, which is a NASA-funded research agency, or that's over here, I don't think, what do you call them? I don't think they're a research agency. NASA-funded agency over on the East Campus off 30th Street. And these guys fancy that they're a bit of Green Central. They take satellite download, they process that, and then they distribute it to government and other customers. And so they're taking pictures of polar ice caps and glaciers and whatnot. Well, they've got a data center there, but they were using old technology, and they said, gosh, we need to be a lot more efficient. They came to us, we helped them design a system in conjunction with a local engineering firm, and we put 8 of our units on the floor here of their data center, and kind of off camera right over here is the data center racks. Hot out, cold out system, 8 of our units, bringing in fresh air from the roof, cooling with our units, air comes out the back of our units, cools the space, takes full advantage of free cooling in the winter and cooler months, and uses our units when they can't take advantage of that, 85 to 97% reduction in energy consumption in a data center. That's a lot of energy saved. That's a really dramatic impact. In fact, they have a live data monitoring of their power consumption. It's on our website. Very, very cool. Plus, one extra feature of this is I mentioned that the working air from our unit here is a saturated airflow. That means it's humid, just like a swamp cooler would be. In this case, what we can do is we can take some of that airflow and put it into the data center so that when it gets too dry outside, we can increase the humidity level inside the data center, which is advantageous because you want to avoid static inside the data center. So potential uses for that airflow. So this is a beautiful setup. This is spectacularly efficient data. So they say it's the coolest, greenest data center in the world. A lot of people say that, but this one's extremely efficient. We can arrange tours for this too. Sorry? Yeah, power utilization effectiveness, and that's a common metric in data centers for how efficient the data center uses energy. 1 is the perfect. Typically, data centers are in 2.5 range. This is much, much better. Yeah, here's another one. This is another little data center. This happens to be in Cheyenne. This is a privately owned data center. It's a colo facility, so people come and pay them to put their servers in. These guys are growing, and as they grow and add customers, our technology is modular, so they just buy more and add more as they're growing their data center. And again, this is not a government funded. This is a few people that own this thing, and this is putting thousands of dollars a month in their pocket. So very real payback, nice energy save, and a good commercial customer, saving them a bunch of money. Now, because our technology does not add humidity to the airflow, you can uniquely use it with existing mechanical air conditioning equipment. Now, typical, like a swamp cooler, you wouldn't want to use that with an air conditioner because it's going to bring in a bunch of humidity, which the air conditioner is now going to spend a lot of energy to pull out. Ours doesn't add that humidity, and so you can use it in what we call a hybrid fashion. So think about a space in Phoenix, and you got some fresh air you got to pull. Well, if you got to pull fresh air off the roof in Phoenix in July, it's 120 degrees. If you've got to pull that in and cool it down to 55 degrees, it's going to take a lot of energy. If by contrast you would put one of our units in front of an air conditioner and do all the fresh air, we're going to give it, say, 70 degree air, greatly reducing the sensible temperature brought into the unit and saving a whole bunch of energy. So this is an example of a way you can use this in a hybrid type application. And in that case, I would point out not as big of energy save as a data center. We're getting a 30–35% range, but it gives you a 3 to 5 year payback. The reason is there's not as much heat load in a retail space as you find in a data center. A couple other small company here in town, a small grinding facility. Nice reduction in energy. They can use it because they grind precision metal parts. They don't want to spend the money on mechanical air conditioning, but they can't tolerate the humidity of a swamp cooler because they're grinding metal parts and it would cause rust. So, real quick summary. Up to 90% more efficient air conditioning than standard. Can use it with existing mechanical systems. Applications are going to be best where you have a high consistent heat load. Data centers, industrial processing, plastic injection molding, things of that nature, or high outside air requirements, hospitals, open spaces that require a lot of fresh air. So those are the places where we will add a ton of value and have a very fast payback. And we'll have this open later for everybody to look at. Thank you.
Great, thanks, Tony. Well, I was really impressed that you guys were saving us 90% of energy use, but now I just found out that it's because you're working with a data center that's measuring the Arctic and the iceberg. So clearly we just have less data to work with.